Hi everyone. I want to talk a little bit today about indeterminate forms and L'Hopital's rule. I really like this topic because it's one of those topics in calculus that deals with infinity a lot, and that infinity is a concept. And you may have heard that infinities have different sizes, right? Certain infinities are bigger than other infinities. And this is one of those situations where those two infinities compete with each other. And we can kind of see which ones are larger and how that plays out. Um, it's got to do with limits, so I'll start off with an example, and we can talk about that one. So this is the limit as x approaches 0 of x times 1 over x. And if we just try to plug in, it's always the first thing we should try to do, is just plug in this 0 here and see what happens. So to me, this looks like 0, right? X equals 0. And then we get a 1 over 0 here. So, and you may have thought of this, this is sort of like 0 times, if this number is positive, then you may have seen this expressed as infinity. So we want to figure out what this is equal to then, right? And you can make a couple arguments here, right? One of those things is that 0 times any real number is 0, so maybe it's 0. We've also got infinity times anything is usually infinity, so maybe it's infinity, or that's quite a wide range that we have there. Maybe it's something in between. Or maybe it's just going to stay a question mark. Maybe it just doesn't make any sense at all to have this. It turns out that this form of a limit is what we call an indeterminate form. So let's say indeterminate form. And if we have these indeterminate forms, then one strategy that we can use to solve them is to use L'Hopital's rule. So we'll look at that a little bit later. But for now, I just kind of want to think about what this 0 times infinity looks like. So if you ever want to find the area of a rectangle, right, that's always length times width, right? So I'd like you to picture a rectangle that's got a height of 0 and a length of infinity. Again, you can make the argument maybe this rectangle has an area of 0, maybe it's got an infinite area, right? It extends forever. And you have this idea of the limit too, so it's a number that's getting very, very close to 0 and very, very close to infinity here. That's kind of what makes this an indeterminate form. Something like infinity times infinity, all right? Infinity times infinity, that's not an indeterminate form. That's just equal to infinity, right, as a concept. So we don't always have to play these games where we have them compete. But 0 times infinity is one of those indeterminate forms. I don't want to wait any longer before I spoil what the answer is for this. The limit as x approaches 0 of x times 1 over x is equal to 1. And I'll show you how to do that using L'Hopital's rule a little later on, but you can at least think of this as being like the limit of x over x. The x's cancel out, right? So you're just kind of left with a 1 there. So these infinities, x and then this x down here, they're the same size. On the other hand, if I have something like, let's say the limit as x approaches infinity of, let's say, e to the x over x. So if we look at, kind of do the same thing we did the last time here, we can say that this up here, if we plug infinity in, we're going to get e to the infinity is just infinity. And then down here, we're also going to get infinity. Just like the last time, this infinity over infinity, or sometimes this is called 0 times infinity, right? We can break it up into infinity times 1 over infinity, is an indeterminate form. So we, this time, rather than just telling you, I'm going to show you L'Hopital's rule. So we'll say anytime we have an indeterminate form, anytime we have an indeterminate form, we may apply L'Hopital's rule. I think that's how you spell his name. Yeah, basically L hospital. We may apply L'Hopital's rule, which states that the limit as x approaches a of some function is equal to this limit approaching the same number where we take the derivative of both of these functions. So what this is saying in this prime notation, right, just take the derivative. So here we're going to take the derivative of the top part and the derivative of the bottom part, and whatever that result is going to be the same limit as this piece here. So let's try that out. But again, importantly, we need to have an indeterminate form. We can't just do this anytime we have a limit. So let's look at our example that we had. We've got the limit as x approaches infinity of e to the x over x. By L'Hopital's rule, first thing we want to say is that's an indeterminate form. Right? We need to have an indeterminate form before we do anything with it. So we can say that this is equal to the limit as x approaches infinity of the derivative of this piece over the derivative of x. So the derivative here is e to the x, right? Easy derivative, and the derivative of x is equal to 1. So we get the limit as x approaches infinity of e to the x over 1, which is just e to the x. Now we can maybe just plug in here and see what's happening. We've got limit as x approaches infinity. We plug infinity in here. That means it's infinity. Depending on your teacher, they might want you to say that it does not exist. Right? Doesn't exist. The reason is it's infinity. Infinity is a concept, not a number, so it doesn't exist. I want to look at one more, and I bet you can intuit this one. But the idea here is that you can apply L'Hopital's rule as many times as you want, and it's always going to hold true. As long as you always have an indeterminate form, you can continue to use L'Hopital's rule over and over and over again. So let's say that we've got the limit as x approaches infinity of e to the x divided by x to the 100th power. So again, we sort of have these competing infinities, right? This one's definitely going to be infinity, and this one's definitely going to be infinity as well. So we want to figure out which of those infinities is larger. And this is certainly a very large infinity, right? Much larger than x would be. But this is also a very large infinity. So I'd like you to picture what would happen if we applied L'Hopital's rule once. The first time we apply L'Hopital's rule, that would look like the limit as x approaches infinity. We can say by L'Hopital's rule. Sometimes you'll see this notation here to say it's equal to this piece by L'Hopital's rule with the uppercase H here. So this would be e of x 100 times x to the 99th power. And we still end up with an indeterminate form. And we could continue this process over and over and over and over again. Eventually, what are we going to end up with? We're going to end up with this stays e of the x unchanged every single time we apply L'Hopital's rule. So if we say maybe 100 more iterations of L'Hopital's rule, if we do this 100 more times, then what we'll end up with is we get the limit as x approaches infinity of e to the x over 1. This, in turn, is equal to infinity, does not exist. All right, the example that I want to leave you with, I'll let you figure it out on your own, but this is a very interesting one to think about. I want you to think about the limit as x approaches 0 of sine of x over x. So give that one a shot, figure out what the indeterminate form is, and I will talk to you later. All right, have fun.